The first speaker is Koichi Hamaguchi from University of Tokyo. He discussed about some new approach for the detection of supernova action. Please start.
Okay, thank you very much. So can you hear me?
Yeah, okay.
Yeah, okay. Okay, so yeah, thank you very much for the introduction. So today I'm going to talk about the supernova scope for this supernova action search. And this talk is based on this work 1.5 years ago with Xiaofan and Jiamin from TDD and Natsumi Nagata and Yoshiki Kanazawa from Tokyo, and 3 experimentalists from Tohoku, Koichi Chimura, Koji Shidoshiro, and Yasuhiro Kishimoto. And actually, I think some of them already gave the same topic talk in different workshops. So maybe some of you have heard the same topic already. But anyway, I talk about this topic. So let me start from this photo. So this is supernova 1987A. The right one is before the explosion, and left one is the supernova itself. Actually, it's 35 years ago this month, February. And before this explosion, seen by the visible light, few hours before this neutrino burst was observed at Kamiokande or other detectors, about 10 or tens of neutrino bursts within 10 seconds. And this, of course, was a big discovery, both for neutrino physics and supernova physics. So what if the next nearby supernova occurs? What if something similar, hopefully even closer, supernova happens, even maybe within our life or maybe after that? I don't know, but what if then? So we could, of course, learn a lot about neutrino physics, also supernova physics, but maybe we can learn more about physics beyond the standard model. So today I want to show one example that nearby supernova may tell us about also axions. So this is the main message of today's talk, and actually this is a summary slide. So I will end with the same slide at the end of my talk. So if a nearby supernova, say within a few hundred parsec occurs, then a huge number of axions will arrive at the Earth. Of course, a huge number of neutrinos will arrive, but maybe also a huge number of axions may come. Then those supernova axions may be detected by an axion supernova scope, which we kind of proposed with the help of pre-supernova neutrino alert. Actually, the same idea, basically the same idea has been already pointed out, discussed by these papers briefly, but we made it a little bit more detailed and also a possible configuration of detectors. And then we found that in a very optimistic case, this kind of supernova scope may see order 1 or order 10 supernova axions if it occurs nearby by extended experiment based on the next generation axion helioscopes, such as the IAXO. So I will also explain this figure at the end of my talk. So this is the main message. And actually, if you already got the idea from this figure, then the rest of my talk is all detail. So yeah, I think the main part of the talk is very simple. Okay, yeah. So this is the plan of my talk. So I briefly explain the motivation or the axion. And then the main part, I talk about this supernova axion, supernova scope. Okay, so let me start from the motivation. So yeah, maybe I should start from this. The strong CV problem is one of the biggest puzzles in particle physics. And it says that the linear combination of this theta term, guru tilde, and the phases of quark mass should be less than 10 to minus 10, essentially 0. And since the quark mass is probably have phases originally because of the CKM physics. It's very strange, unnatural that this linear combination of them have vanishing value, almost vanishing. And this fine-tuning problem cannot be solved by anthropic argument, at least in the minimal setup. So this is in some sense the most serious fine-tuning problem, one can say, I think. Compared to Higgs and dark energy, those problems may be solved by anthropic argument, but the strong CP cannot. And this strong CP problem can be solved by this Petrarchian mechanism that predicts a very light particle axion. And this axion field is a promotion of the theta term by the dynamical field, and also it can be the dominant component of the dark matter. Actually, I think this is one of the dark matter session talk, but my talk, in my talk, at the end, the parameter space of interest, axion in a canonical sense is not the dominant component dark matter. But anyway, the following discussion can also apply to axion-like particles, ALPS. So in that generics context, dark matter physics may also be related to this supernova axion. Anyway, and then these axion couplings are determined by decay constant Fa. Essentially, all couplings to gluon, photons, leptons, quarks are determined by 1 over Fa, depending on this order-1 couplings, depending on case physio DFSC models. And mass is also determined by Fa. So basically, very roughly speaking, in this QCD axion, all parameters are determined by this one Fa, up to order 1 model parameters. And there are many constraints in this Fa or in axion mass from various stellar cooling constraints, also direct detection, and also cosmological argument. Actually, I think there are several related talks in this workshop on this axion model, axion cosmology, and so on. And there's also hint from stellar cooling around here. And today's my talk also at the end, it's focusing on this region, 10 to 8 GeV-ish decay constant value. At the boundary of the constraint, also around the stellar hint value. So in that region, the two severe constraints are from Supernova 9087A, about 10 to 8 GeV, also neutron star cooling, also from around 10 to 8 GeV. And also around the same value, there's a stellar cooling hint that says that the various stars show anomalous cooling, which might be explained by cooling by the axion. And actually this value, preferred value from the stellar cooling is already in tension with this constraint. So if you take these values literally, then it's slightly disfavored already. But I should say these bounds also have various uncertainties. So in any case, the value around 10 to 8 GeV is, I think, interesting at the boundary of the constraint, also stellar cooling hint. So it would be nice if there's more direct way probe of those axions from stellar objects. And supernova can be such a direct probe. Okay, so 10 to 8 GeV is the parameter range of interest. Okay, now let's talk about supernova axion detection. And first I start from supernova candidates. So actually there are some very close supernova progenitor candidates. One is, for instance, Antares here, 170 parsec, or Betelgeuse, it's 200 parsec from the Earth. And if we concentrate on the stars, the red and blue giants, within the distance of 250 parsec, because otherwise, if it's too far, at the end, the number of axions is too small. So we concentrate on really close candidates. And we also concentrate on the candidate stars with mass heavier than 10 solar mass. I will explain the reason later. But anyway, if we concentrate on this heavy rather heavy progenitors, candidate stars, and also close distance candidates, then only 6 of them remain. So the closest one is Spica, 77 parsec from us. And the farthest among them is the Betelgeuse, 200 parsec from the Earth. All of them have mass around 10 or 20. And we also know the position on the sky very well. All right. So now, so those are the candidates. Now let's talk about the supernova scope for the axion. So suppose that in the future, nearby supernova, one of them really goes to supernova explosion. And then actually a few days before or days before this explosion by the visible light, because they take some time to escape from the remnant of outer part. But before that, we have a neutrino burst. And like in 1987A, they will arrive, of course, Earth. And like in 1987A, we will see a neutrino burst then. And since now we have better detectors around all over the world, so that will be a fantastic, I think, signal. So we will learn a lot about neutrino physics, supernova physics, many things. And huge number of neutrinos will be detected. But now if we have also axion, then they may also be emitted from the supernova on the same timing, in the same 10 seconds. Actually, in particular, this axion proton or axion neutron coupling can give this kind of diagram. So Bremsstrahlung. So and this 1/FA coupling to proton neutron, axion can be emitted from the same physics, same supernova explosion. Then, depending on the decay constant, a huge number of axions are also produced, and some of them also arrive at the Earth. So we want to see such an axion by something. And one possibility is use this magnetic field. So because of the axion photon coupling, under the strong magnetic field, axion can be converted to a photon. So I should mention that this production part is axion nucleon coupling, but axion detection part in this setup is axion photon coupling. Yeah. So, but now this axion photon conversion, if you know this kind of, if you see this kind of configuration, maybe you notice that it's essentially the same as axion helioscope. So there is already an ongoing experiment or next generation experiments, planned ones, that trying to see the solar axions. So axions can be produced from inside the sun, and then those solar axions can be converted to a photon under a strong magnetic field, and then those experiments are already ongoing with this very strong magnetic field and about 10-meter length, and then meter squared or the area, detection area. So then, because we already have this strong magnetic field coil and this kind of system for ongoing next generation experiments, so it would be better if we can just use it also for the for the supernova axion. But there's one big difference, that's the energy is different. So in the case of solar axion, its energy is about keV, simply because of the temperature of the sun. But for the supernova axion, it's about 10 or 100 MeV, again, because of the temperature of the supernova. So this axion helioscopes, already it is ongoing experiments, they use this X-ray detector with X-ray optics, this focusing system. But if you want to use this system for the gamma ray, much higher energy, probably it doesn't work, or it's very difficult, because at least this focusing optics doesn't work for gamma ray. Also, the measurement of the gamma ray energy, it will be difficult with this system. And then probably I don't have time to explain, but the background rejection is difficult. So it's better to have a gamma ray detector for the supernova axion. So on the one hand, we have X-ray detector already for the solar axion. But on the other hand, we want to have a gamma ray detector if supernova axion will come. So our idea is to put the gamma ray detector in the opposite end to the X-ray detector with the same magnetic coil, but two ends having two detectors. This side X-ray detector and this side gamma ray detector. It's a very simple idea, but I think it's interesting. So in the normal operation time, it works as an axion helioscope. So it just follows the sun. And in this time, this gamma ray detector doesn't do anything. The axion just goes through it because it's extremely weakly interacting, and very small fraction of them might be converted to photon under the strong magnetic field. So in this situation, this gamma ray detector part is nothing. But once supernova occurs, and if we can point this part towards the exploding supernova, then now this axion might be converted to the photon, and then this gamma ray can be detected by this detector. And in this situation, of course, this then X-ray part doesn't do anything. Axion just goes through it, and this gamma ray detector might detect this signal. So this is one of the ideas of this supernova scope, putting two detectors in the opposite side. Okay. Okay, now I want to talk about pre-supernova neutrino. That is also very important for this proposal. So in order to detect this supernova axion, we have to point this experiment towards the exploding supernova. But supernova axions come within very short time, like 10 seconds. So if you remember this 1987A signal, neutrino burst is around this 10 seconds. So axions are also essentially coming from the same time window. So it's very short time. So we have to know in advance when it comes. So how do we know that the timing? So we can now take the help of pre-supernova neutrinos. So this figure is from our collaborator Ishitoshiro-san. He's an expert on this physics. So this x-axis is the time, and 0 corresponds to the quark collapse, the supernova starting. And y-axis is the neutrino luminosity. And as I said, before the visible light, already neutrino, the quark collapse happens before that. And right after this, you can see a huge number of orders of magnitude increase of the neutrino flux. So this is the supernova neutrino burst seen in 1987A supernova. And axions also expected to come from the same window, time window here. So we want to know when and where it happens before this. But now if you see this neutrino flux, although it's orders magnitude smaller than this peak, you can see already increase of the neutrino luminosity. So let's say seconds or hours or days before the quark collapse, already the neutrino flux are gradually increasing compared to the normal time. So if you can see such an increase of the neutrino luminosity towards the end of the star evolution, then we can somehow predict that supernova may happen. And this kind of thing has been studied, and these are typical figures. So these are the cumulative number of expected supernova, pre-supernova neutrino events for an ion core progenitor with a distance of 200 parsecs. So this is the typical situation for Betelgeuse, for instance. And this x-axis is the time to collapse. So this is, so 0 corresponds to the core collapse, and this this part corresponds before the explosion, before the supernova. And green one is the mass, this progenitor mass of 15 solar mass, and this is 12 solar mass. And these lines correspond to inverted normal hierarchy and so on. For super K, Cameland, and future hyper K Juno. So for instance, Cameland, hours or before the explosion, already tens of neutrinos will be can be detected, and that can be above the threshold, above the, how to say, the background normal operation time neutrino flux. Then you can say something anomalous is happening. So maybe something supernova may happen. And this kind of actually study is now, they have a global network, not only these experiments, but also Dune, Snow, all of them somehow collaborate to how to say, to say each other that this kind of anomalous neutrino flux. So it's called Supernova Early Warning System, SNEWS, and they can trigger, they can alarm each other that neutrino flux is increasing. And according to their study, hours or days before the explosion, if the distance is close enough, pre-supernova neutrinos can be detected. I mean, it can be above the threshold, and they can trigger a lot. So yeah, in those nearby supernova cases, we can know that hours or days before the explosion, the timing. And one thing, important point is that if the mass is too small compared to less than 10 solar mass, then it turns out the neutrino flux is too small to be detected, even for this nearby candidates. Therefore, we discarded these light progenitors and concentrate on these heavier ones. That's why we chose this, just 6 of them. Another important point is that although it's very difficult, it's in principle also possible to estimate the direction, location of the candidate. So this figure is from this previous analysis. In the case of Betelgeuse, 1 hour before the explosion, by this neutrino signal, this Juno can estimate the direction of this pre-super neutrinos within this range. And if you add the lithium, they can also even narrow down the direction and can say those coming from this kind of area. So hopefully we can also know the direction, not only the timing, but the direction of the supernova. So of course, I mean, it depends. I mean, if it's, let's say, if we can say it coming from here, then we can concentrate on this guy. But if we can only know it coming from this area, then we have to maybe bet one of them, one of the 2 or 3. But anyway, yeah, overall, there is a chance that we can see roughly where it's coming from. So the optimistic scenario is that one of those or some of them trigger this SNEW system, pre-supernova neutral alert. Then this supernova scope, looking at the sun, temporarily move in the other direction and wait for the axion conversion. So that's the optimistic scenario. Okay, now I want to talk about also the time fraction. That's also, I think, important. So if we want to use this axion helioscope, then they can move 2 pi in this horizontal direction, but it can move only to a certain range in the vertical direction. because for the helioscope, for the solar axion, that's sufficient. And numerically, it's like plus minus 25 degrees for IXO, or another experiment taste, it's plus minus 20 degrees. So if the supernova happens, in this situation, then we can of course wait for the axion. But if we are unlucky and the detector is in this position and supernova is here, then although the axion is coming, you cannot point this detector towards this supernova. So we wanted to know how much time fraction we can point to this certain stars. That's very simple calculation. So we took altitude of the progenitor stars, those 6 stars, seen from Hamburg, because the IXO is the candidate site is DESY. So this x-axis basically corresponds to 24 hours Earth rotation, and y-axis is the altitude of those 6 star candidates. And these lines are the motion of these stars. And this gray bands, plus minus 25 degrees, corresponds to this maximum elevation of detector. So if the stars are within this band, let's say like here, then you can point. But if it's outside, unfortunately, the detector cannot point to that star. So overall, we see that the observation time fraction is more than 50%. So more than 50% of the time, you can always point detector towards a certain star, except for this green one, Alpha Lupi, this one. But since the supernova itself is very rare event, maybe not within our lifetime, so it's very rare. So we don't want to miss such a rare event. So we can increase this time fraction by 2 ways. One is simply, of course, increasing maximum elevation. So if you take the maximum elevation angle from 25 to 50 degrees, then time fraction. So this is again 24 hours Earth rotation, and these are the 6 candidate stars. And light blue corresponds to 50 degrees of plus minus 50 degrees is elevation. So you can see, of course, time fraction increases. Also, another possibility is to put another detector in different place. Just to give an example, for instance, if you put it Tokyo, then it plays a complementary role. You can see that now, if both of them have elevation of 50 degrees, then 100%, 24 hours, always you can point the detector to one of them. Yeah, so those are the possibility to increase the time fraction of the pointing. Okay, so finally, I want to discuss the event number. Maybe I finished too early, but anyway. So event number estimate is very simple. Total number of axion event detector is total number of axions from single supernova times this area fraction times the axion photon conversion probability. And the first factor is actually most difficult and actually most uncertain. But we at the end, we took simply the detailed study from previous work, this one. Actually, there is an update after this work, but at that time, we simply took this paper. And this paper includes various corrections to simple 1 pion exchange approximation. And this is the kind of fitting formula for the axion luminosity. It's 1 over FA squared, coupling squared, and it also includes the other one parameter from the axion nucleon coupling and axion proton coupling, depending on case VZ, DFSZ. And we also include the temperature dependence, simply read from the fitting formula. And because we are interested in the axion number, we have to divide the luminosity by the axion energy. But axion energy actually is rather, how to say, robust or stable. This figure shows the axion energy distribution in units of temperature for various modeling of this axion emission. But you can see all models say that the axion energy is about 2.3 times temperature. So this part is rather robust. So at the end, axion number is axion luminosity divided by axion energy times the duration, how long this burst continues. And it's given by this formula. It's 1/FA squared. And here we took the case VZ coupling for the proton-neutron coupling, and we took 10 seconds of duration, and then typical temperature of the supernova. But I have to say this temperature dependence has a rather strong dependence. Also, this factor can have order 1 or maybe even factor 10 uncertainty, because there are various uncertainties inside. Anyway, this huge number of axions can be produced from the supernova for decay constant at the boundary of the constraints. Now the next factor is simply this area. So it's 4 pi distance squared and the area of the detector, and that is very small fraction, but we cannot do anything. It's simply because the supernova is too far. So for 150 per sec away supernova and the detector area of meter squared, which we take from this IXO experiments, then only this fraction of total number of axions come to that detector. But still, compared to this 10 to 57, we still have a lot of axions coming to this detector. And finally, this axion photon conversion is also a very small number. And now this, I think this part many of you know well. It's inversely proportional to FA squared, magnetic field squared, and length of this magnetic coil squared. So again, we take FA 10 to 8 GeV and case VZ coupling, and magnetic field taken from IXO, few Tesla, and the length of this detector 20 meter, again from IXO. And there's also one additional factor that if the axion mass is large, or if the axion energy is small, then this Q parameter becomes large. Then axion photon conversion should be taken into account. And in that parameter space, this factor also gives additional suppression. But if the energy is large enough, or if the mass is small enough, then this factor is essentially 1. Then it's simply coupling squared, magnetic field squared, length squared. And this probability is 10 to minus 20. So altogether, if you multiply these 3 factors, it's about order 1 at the end. This kind of rearranged the parameter dependence. This is axion model dependent part, 10 to 8 GeV coupling with KSVZ order 1 parameter. This part depends on supernova, distance, duration of the burst, and the temperature. And finally, this part depends on detector, the area, magnetic field, and the length. And as I said, especially from supernova part, this number can have order 1 or about factor 10 uncertainty. It may have. But overall, we may have order 1 event in the detector. So this is a plot for the sensitivity. So this is the axion mass. This is axion photon coupling. And for the axion coupling, we took case VZ model. I mean, so we simply, rescale the axion photon coupling to axion nucleon coupling, assuming case VZ model. So these, of course, order one parameter. between the axion photon coupling and axion nucleon coupling. But to show this in this two-dimensional plot, we took the axion mass to be free parameter. So in that sense, this figure can be regarded as a axion ALPS-like figure, because axion mass is in this figure not related to the couplings. And this green lines correspond to the QCD axion, and the other parts correspond to more generic ALPS axion-like particles. This blue-red lines are the numbers, contours of, say, one supernova axion event or 100 supernova axion. For the closest one, Spica, 77 per sec, and the Betelgeuse, 200 per sec. So you can see it has a better sensitivity in the than the helioscope. Sorry, this part is helioscope. This cast, this blue one is already excluded by the cast experiment, and this orange and light green ones are the prospect or sensitivity of the future experiments for the solar axion. And these blue-red lines are the supernova axion. So you see supernova axion possibility have a better sensitivity for heavier mass. This is because the supernova axion has a higher energy compared to the solar axion. Therefore, this suppression factor, or this one, or this Q value, is different for the same mass. So the suppression factor becomes important earlier for the solar axion, but it becomes later, or how to say, it's extended to heavier mass for the supernova axion because it has a higher energy. Also, you can see in the low mass region, in the very optimistic scenario, we may see both solar axion and supernova axion with the same setup. Okay, I have to also mention that this is a stellar hint parameter space, stellar cooling hint. And in this figure, I didn't show the stellar cooling constraints. And if we superimpose it in a different plane, it goes like this. So in this figure, axion mass is fixed to be light, 10 to minus 3 electron volts. So it's essentially irrelevant. And x-axis is axion nucleon coupling, and y-axis is axion photon coupling. And this green and yellow are the case VZ and DFSC. Now, since the supernova scope sensitivity depends both on the production and the detection, the nucleon coupling and photon coupling, it goes this way, diagonal line. So this dashed lines are the 100 events and the solid lines are the 1 event. On the other hand, this cooling constraints like neutron star or supernova, it's constraint on the axion nucleon coupling, and actually it's around here. So if you literally take these bounds, then actually most of the regions are already excluded, and only this how to say marginal point, case VZ case, in the closest one, Spica, you expect just 1 event. However, I should say, as I said, this constraints also have uncertainties. So we may have more events. And one comment is that, for instance, if you take this supernova bounds and supernova axion, you might think if you, use the uncertainty to lose the constraint, then you may also lose the event number. But one difference is that the constraint case, it's production, so 1 over FA squared. But for the supernova scope case, it's production times detection, so it's 1 over FA to the 4th power. So in that sense, parameter dependence is different. So if you parameterize this uncertainty by this C error, and if you go one of the two directions this way, then the bound becomes weaker still, while the expected number doesn't change so much. And if the uncertainty factor is about order 1, smaller than the nominal value, then order 10 events may be possible. And of course, we can always think about the beta detector to see how to say further candidates. Here we concentrate on the closest one within 200 parsec. Yeah. Okay, maybe it's too early, but let me summarize. So this is the same slide as the very beginning. So if a nearby supernova occurs within a few hundred parsec, a huge number of axions, in addition to neutrinos, may arrive at the Earth. And this kind of supernova scope with this configuration may be able to see such supernova axions with the help of presupernova neutrino alert that tells us the timing and the position of the supernova, possibly. And that this kind of supernova scope has a potential to see order 1 or order 10. Maybe 100 is too optimistic. Supernova axions in certain parameter space. And anyway, such a nearby supernova is extremely rare event. I think it's much less than once in century, unfortunately. So it would be a once in a lifetime opportunity. So yeah, and then it would be better if we can also see axions, not only neutrinos, from that kind of rare event. Okay, thank you very much.
Okay. Yeah, thank you for the nice talk. Yeah, so we have enough time for question. Yeah, is there any question?
So Koichi, I have a question.
Yeah.
So if we can build two detectors to monitor 6 supernovas, how much we can gain in chance to detect the signal? Instead of 1, if we build 2 detectors, how much we can get?
That
because we need to you need to move the whole detector within, say, 10 seconds, right?
No. That's the point. That's the thing. So I mean, where was that? So hours or days before the explosion, we know.
Okay.
Yeah.
I see. Okay. Yeah.
But direction is very difficult. Is very difficult. Yeah.
Right. Okay. I see.
Yeah.
So even we can build 2 detectors, we don't get much.
Well, I mean, depends. So even if we know the position, if we are unlucky like this one, we cannot point. So in that sense, it's better to have at least 2.
Okay.
Because then we can cover the 100% time.
I see. Right.
At least, yeah.
I see. Thank you very much. Very interesting. Thank you.
Another question?
Yeah. Thanks for the talk. Was there actual data analysis of Kamiokande, original Kamiokande 1987A data for axion search?
Axion, yeah, that's very interesting question. And there is an analysis proposal, but direct detection of axion from supernova, super K or hyper K is, I think, difficult, and you need a completely different analysis. And for super K, I think there are analysis, but the obtained bound is much weaker than the simple neutrino analysis. Yeah.
I see. Is it mainly due to the magnetic field that's required?
This one is uses the magnetic field, and I didn't explain, but essentially you can set up, I think, almost background free situation. So you cover something to withdraw the backgrounds. And in this situation, there's almost no background. But for super K, hyper K, they come the huge number of neutrinos and axions at the same time. And the axion, even if it's something, it gives a completely different signal. Not this like, there's no magnetic field, yeah. So it's difficult and different situation, yeah.
Well, in that regard, can I ask one more question?
Yeah,
I
yeah,
just
yeah.
thought of. How about you install just variable magnetic coil, for example, so that you can have full detector such as super K size detector, but you install somehow magnetic field surrounding the detector.
Surrounding super K?
Yeah, something like that.
I have no idea, but naively, I think already this size, this few Tesla magnetic fields is very, challenging. So I guess it's very difficult to cover the hyper K by super K by magnetic field. So one thing, I should mention is inverse Primakov. That's one possibility, and actually we thought about it in different paper. So this inverse Primakov, I think this xenon low energy recoil, you remember, one possible interpretation was like that. So we estimated the number of axions from signal from this kind of process, but then for super K, hyper K, it's 1 again with the same parameter set. And in this case, we don't have to point the detector because hyper K is hyper K, but we think it's difficult to distinguish from backgrounds because hyper K, of course, will see a huge number of neutrino events at the same time. And just one axion single photon among this huge number of neutrino bursts, that probably is difficult. Yeah.
Yeah, it will be a happy day if you have neutrinos as a background.
Right, yeah, of course, yeah, sorry, yeah, for axion, it's back, yeah. This will be a fantastic signal for neutrino physics, yeah.
Yeah, thanks for the answers.
Yeah.
And I think we have more question from Masaide.
Hello.
Hello.
Hello, nice to meet you. Yeah. I have a simple question for this slide too. So, event number it strongly depends on FA.
Yes.
And the power is 4.
Yep.
And from the cosmological viewpoint, FA and the 10 to 8 is a bit small.
Yeah, for dark matter, yes. That's
so
right.
Do you have some comment on even one order up 10 to minus 4?
Event. Right. Yeah. So I think in generic axion-like particle modeling, maybe it's possible to have a model that gives a dominant component dark matter and supernova signal.
Mm-hmm.
But in the minimal QCD axion, like conventional case VZ or DFSC, then mass coupling, everything is related. So as you said, this parameter space is not related to dark matter in that sense, unfortunately.
I see.
Yeah.
Okay. Yeah. I see. I understand. Okay. Yeah. I got to know that. Yeah. Honest opinion. So okay.
Yeah.
Thanks. Yeah. Okay. Good. Thanks. Thank you very much.
Okay. Is there any other question?
I have a short question about the production mechanism for action. Have you thought about different production mechanism other than nucleon?
Haven't studied in detail myself, but I know. Sorry. Why? Sorry, I stopped sharing. Yeah, so I noticed think Eung Jin, for instance, did one of those. Where was that? Oh no, sorry. just 1 second. Yeah, so this paper we took as a reference for the production. It's 19, but after that, there are several updates or more works. And for instance, this one, if I remember correctly, perhaps some of them are in the audience, took into account axion pion coupling. Sorry, I have to look, but yeah, another production mechanism. Yeah.
Still, it depends on the nucleon coupling.
Right. Yeah. Yeah. And axion electron coupling and other couplings are also studied in the
electron or muon.
Yeah. 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 But in the conventional QCD axion, the nucleon coupling gives dominant production. Yeah. But in generic ALPS, you can think about different production mechanisms as a dominant source.
I see. Okay.
Yeah.
Thank you.
Okay, it's time to move on to next question. Yeah, thanks again to Koichi Hamaguchi, nice talk.
Thank you.
And then let's move on to the next speaker. So next speaker is Professor Eung Jin Chun from KIAS. Are you there?
Yes, you hear me?
Yeah.
Okay, so how can I so this is my screen.
Yeah, you can see. So next speaker is Professor Eung Jin Chun from KIAS. Here discuss about scalar dark matter content by thermal fermion. Please start.
Okay, so thank you again for the nice kind invitation to this workshop. So today, so I'm going to talk about some new way of generating ultralight scalar dark matter. And then we'll hear more about this later in this workshop from Brian Patel as well. So the brief introduction. So, I mean, recently ultralight scalar field is considered as an attractive candidate for core dark matter. But the question is how to produce them in the early universe. And typically for dark matter mass around 10 to minus 20 electron volt, we need to populate them, around the order of 10 to 20, which is a huge number. Of course, we know a very nice mechanism called the misalignment mechanism. So somehow we assume that this scalar field got a constant amplitude in the beginning, then later it will give us some coherent state. So of course, the first nice example is the QCD axion, which has very flat potential through instanton dynamics. So today I'm talking about a new way of generating this coherent scalar dark matter state driven by tiny couplings to thermal fermions. Okay, so brief review on misalignment mechanism. Actually, coherent state of scalar, quantum scalar field is nothing but classical wave. So here we have the scalar field and then annihilation and creation operator. So I am assuming the real scalar field. Then the medium expectation value give us just a C number, like a constant amplitude and wave-like particles, right? So here at present universe, we know the number density of dark matter, then it will determine the size of the amplitude, which is roughly given by this quantity. So in the early universe, expanding universe, in the thermal background, this amplitude can depend on the time or temperature. So it should follow, for the free field, it should follow this evolution equation, as we know. Then typically for Hubble parameter larger than m5, so this is a huge friction, so phi remains constant. So initially, we arranged some constant value. And then later, when Hubble parameter becomes small, or t, m pi t becomes much larger than 1, this part can be ignored. Then we have free oscillation. I mean, this is harmonic oscillation. So then by having this initial condition, we can actually solve later time behavior of this classical amplitude. Okay, so I mean, remember that the Hubble parameter of, at the matter radiation equality is around 10 to minus 27 electron volt. So definitely we need to generate this scalar dark matter population before the equality, so that we have to have the scalar dark matter mass larger than this HEQ. So then from this equation, of course, I mean, you see that the later for m phi t larger than 1, the scalar energy density scales like this. I mean, you know, this is just a cold dark matter equation. Then from this, if we require that this constitutes 100% of dark matter candidate, we can determine the initial amplitude, misaligned amplitude like this. So now, so there's another interesting way of generating this misaligned amplitude, assuming this is scalar field coupling to thermal fermions. So, you know, this F can be either quarks and leptons, or even charged leptons or neutrinos. And then, okay, so this is small Yokohama coupling. So having this interaction, I mean, a long time back, people calculated the effective potential of a scalar field. From this, actually, we can generalize a free field evolution equation in the early universe. So, so actually, the leading order effect comes from the linear in phi and also the temperature dependent mass. So if you expand this, you get these two leading terms. So I will use only these two terms to solve this equation. Of course, you know, I mean, this is thermal, this will determine the thermal distribution of fermions in the background, and then this is thermal mass of scalar field through this coupling. So actually, this interaction was used by these two people to study some non-trivial neutrino evolution at a later time. So because of this, I mean, neutrino can be massive, and then they studied some interesting, they observed some interesting effect. And then also Bartel and his company also got the same idea to use this for generation of ultralight scalar dark matter. Okay, so some generic features. So now we know these two terms. So instead of time and temperature, I will use this parameter x, which is the dark matter mass times time, and then it has it has 1 over temperature scale dependence, assuming the radiation domination error. And then I use a scaled, rescaled scalar amplitude, which is dimensionless. And then M20 is nothing but dark matter mass normalized by 10 to minus 20 electron volt. Then we get this equation. So value of x1, xs, I mean, is given by these quantities. So this is purely model dependent parameters. And then now, I mean, so task is simple. I mean, once you have this equation, you just solve it. So it's easy. We can have very easy solutions. So of course, in the initial point, we assume that there is no initial value for the amplitude and the derivative. And then we'll have this non-trivial evolution from the electroweak time, which is the equivalent x is x electroweak to the TF, when the temperature is same as the fermion mass, the thermal fermion mass, also corresponding X I call XF. Then after XF, basically we can have a free evolution. I mean, temperature below MF, there will be no fermions F. So then the source term will disappear. And then typically, okay, so then from TXF, so these two terms that will disappear. So then we have a free evolution from XF to XEQ. The neutrino case is a bit different. You know, neutrino mass is so small, and then TEQ, I mean, the neutrino mass is a bit, of course, smaller than equality temperature. So for neutrinos, we have evolution from electroweak temperature to equality temperature. So we have different type of solutions. Okay, now, so yeah, typically, so X electroweak is the smallest initial point, and then XF will be will come later, and then finally we come to the equality time. So depending on our parameter values, X1 can be placed here or there. So we can have three possibilities, like X1 even earlier than the initial point, X1 even later than XF, when the free evolution is operating, and then X1 in between. Actually, the case 3, we can have some complicated solution, but for case 1 and 2, I mean, we have only 1 step and 2 step equations. And then, as I said, for neutrinos, actually X1 can place either way, but I find that only in this case we can get the appropriate dark matter density. So I just present this case. So now you solve the equation and then determine the dark matter density at equality time, then it should behave like this. So in this case, like T to the 1 over T to the 3/2, or the temperature cubed, or the expansion and the scale factor to cubed, or inverse minus cubed. And then, okay, XS is given parameter. Then from the solution of this equation, we should determine this coefficient C. So, I mean, of course, this will be the function of the fermion mass, the coupling, and dark matter mass. Then to get the right dark matter density, we need to have this quantity. Okay, so now just for the reference, for dark matter mass 10 to minus 20, X electroweak is around 10 to minus 15, equality time is 10 to 7. So this is quite recent time. And then XF typically placed in between. Of course, it depends on the fermion you take. And then X1, XS, I mean, it's proportional to Y squared, and XS proportional to Y. Also XS, the thermal distribution of fermion depends on the fermion mass itself. So there is a fermion mass dependency here. So if you see this, then the X1 becomes order 1 when Y5 is 10 to minus 20 or 24. So that's the typical value we need to generate the right dark matter density. So later we'll see more exact numbers. Okay, so now, I mean, my approach, instead of solving this numerically, so this is a heavy job for my computer. So I just took the asymptotic regions, which can give me the exact solution like this. So X much larger than X1, actually here, this quantity can be ignored compared to the M phi squared, the 1 here, the originally M phi squared dependence. So if you let a Mathematica solve this equation, then he will give you this funny combination of the Bessel functions and hypergeometric functions, whatever. So of course, there is a homogeneous part. The constant C1 and C2 will be determined by the initial condition. And then also the opposite case, the temperature dependent mass is much larger than the m phi squared. So we have this equation, and the solution will be given by this. So here you see, I mean, in this case, x1, if this number is very large, actually this is nothing, it's almost same as having the vacuum-ited value of the scalar field. So, I mean, this will give some interesting effect in neutrino dynamics in the late time in the cosmology. And then, of course, the free evolution. I mean, we know that this will be combination of two non-trivial Bessel functions like this. Okay, so that's it. So actually, we are done. So let me first consider the case where x1 much smaller than the initial point. Then in the from x electric to the MF, temperature MF, we have this evolution equation. And then after MF, we have free evolution. So we know there are two asymptotic solutions in each regime. Then at XF, I can match these two solutions to determine C1 and C2. So yeah, G1 and G2 is, I define this function like this, what that. Then so you can get this constant C1 and C2. Of course, the first equation is obtained by imposing the initial condition that the vanishing initial conditions. So you see, I mean, it's a function of XF, and then XS given like this. Okay, so then again, in the asymptotic region where XF much smaller than 1 or much larger than 1, I mean, this will give us this simplified form, so that in each case you can find appropriate value of dark matter mass and then the corresponding coupling to get the right electric density. It's a bit complicated, but you don't have to follow all the details, but typically, you know, for M20, the coupling required is about 10 to the minus 24 or 20 minus 7, depending on the different regimes of XF and so on and so forth. Okay, of course, I mean, in some parameter space, the freeze-in mechanism of this light dark matter can work. So I just try to exclude those possibilities. So the free for M phi larger than 46 electron volt for electron, and then Y phi larger than about 10 to the minus 11. I mean, the freeze-in mechanism can also work. So then. Probably in between, we may have some combination of these two mechanisms working together. But in this way, I just concentrate on this thermal mechanism generating coherent state. Okay, so case 2, when X1 much later than the temperature MF, then again, I mean, we have different initial equation between X electric to XF. And then after XF, we have free evolution. Then you match this condition at XF to get this a bit complicated expression. Then taking some asymptotic regions like this, we get, you know, I mean, we determine the CF square, like it's proportional to XF square. This is a funny combination of XF and X1. Then finally, to get right density, you can get these typical numbers, 10 to the minus 24. Of course, all depends on what fermion you take, and then what mass range of M20 you take. So for this range also, I mean, you know, since our dark matter is very light, it shouldn't be thermalized during BBN. So this is the condition that the light dark matter never in thermal equilibrium. Okay, so case 3, complicated cases is a bit dirty set of equations, so just I skip. Finally, for neutrinos. So as I said, I find the appropriate solution only in this case, and then I need to solve these 2 equations, and then of course each case was appeared in previous cases. So this is 2 different set of linear the intermediate asymptotic solutions. Then for neutrinos, this is a bit complicated function for the final the dark matter density number. Okay, so then anyway, C nu squared is again given by this combination. I mean, instead of C1 squared, C2 squared, actually initially we have this constant, right? So this will give us additional contribution to the final dark matter density like this. And then we have some interference between this term and these 2 terms, so that not only a typical form of this, but also we have these 2 additional contributions. So for x1 much less than 1, I can find the solution. So this is just order 1 number. So assuming neutrino mass about 0.05 electron volt, corresponding to atmospheric neutrino mass. So I need equal coupling around 10 to minus 20. So that this M20, okay, of course, to avoid the BBN constraint, we have to set the parameter space below these two numbers. So here, interesting point is that, comparing XS, X1, and XEQ, we get these numbers. So XS is much smaller than X1. And then X1 is comparable to XEQ. So this means that the dark matter can generate it very close to the matter radiation equality time. So this is a way of, during the BBN, we don't have a dark matter relative density at all, but so actually we can generate dark matter density very, very late. Okay, so let me come to the conclusion. So an ultralight scalar can form coherent state dark matter through its tiny coupling to standard fermions. So I studied all the possible cases. Of course, assuming the thermal fermions as charged leptons and quarks and neutrinos, so we have a different set of equations. So you can determine the corresponding parameters, giving you the right dark matter relative density. So for the dark matter coupling to quarks and charged leptons, we need dark matter mass M5 below 10 to 6 electron volt. And then it can be, of course, much lighter than 10 to minus 22, but I took the number quoted by initial fuzzy dark matter paper. Of course, the current bound would be, depending on observations, it could be 10 to minus 20, 10 to minus 80, and so on and so forth. Probably we hear this more about later from Brian Battelle. So the corresponding Yukawa coupling from 10 to minus 28, 10 to minus 8, you can generate the light dark matter relative density. So for phi Nunu coupling, so dark matter genesis works for this range and then this range of Yukawa couplings. And then as I said, so dark matter generation time T can be as small as 10 times equality time, which is about, say, 10 electron volt. Okay, that's it. Thank you.
Okay, thanks, Professor Eung Jin, for introducing new scalar document production mechanism. So, is there any question?
I have a question on the neutrino coupling. In the case of neutrino, I mean, as I understand, you need displacement due to the fact that the thermal correction has a minimum, which is different from the zero, right? The thermal potential, minimum of the potential.
In this case, right? yes, this is the minimum, say.
Yeah. So does it?
But in other case, it doesn't have to be. I mean, this acts as a source term anyway. So starting from 0 to, as time evolves, the phi increases in the general setup. But in this case, in this particular case, the initial, say, low minimum, the vacuum value is fixed. So this is the difference between neutrinos and the other cases.
So actually, I read Brian Bartel's paper, but I want to compare between the two papers.
Yeah.
So that I think the Brian focused mostly on new fermions.
They consider the muons as a.
Did I? I see.
Yeah.
So
actually, so I also compared, and they did the numerical. They found numerical solution, which. And then actually, So okay, so I mean, they applied to muons, and then on the smaller mass range, I mean, their solution agrees with this branch. And then for larger mass, this branch. There is a factor up to factor 10 difference. I don't know, factor 3 or 4 or factor 10. So I checked it, but anyway, these two branches corresponding to these regimes. And then there is some region in between. Probably I didn't check it, but that region may come from this kind of branch and so on and so forth. But this I didn't check.
So typically, in order to get a sizable thermal effect, you need standard model particle or new fermions.
Yeah, it can be any dark sector particle which is in thermal equilibrium.
You need something which is in thermal equilibrium.
That's right.
And the mass must be, I don't know, for QCD, I don't know what is the typical temperature for action oscillation. But the
action oscillation, I mean, this is QCD, so GeV. It's 100 MeV.
So, and the new fermion must be, new fermion was standard on the particles must be lighter than this oscillation temperature, such that the
what oscillation temperature?
You don't want a Boltzmann suppression for the new fermion.
Actually, okay, so I assume the temperature larger than the fermion mass.
Yes.
So that they are in thermal equilibrium. Below MF.
Yeah.
Either their population is suppressed, or most likely they will co-annihilate to photons. This process is very rapid, so they disappear from thermal soup.
Right. Yes. It's interesting.
Jin, do you have an estimate about the radiative decay width of this light scalar particle?
Oh,
through the one.
Yeah, that's no, I didn't.
But you still.
Okay, so yeah, for 10 to minus 20, maybe much, maybe. But yeah, for say about milli-electron volt mass, I don't know. I guess negligible, huh?
Yeah, your Yukawa is tiny, small. So probably
yeah. So I don't know. Yeah. So say let's take 1 electron volt. So what did I say? Okay, so for 10 to 6 EV, I need 10 to minus 8. Probably this, yeah, this part maybe interesting to see the phi to gamma gamma.
Yeah.
Oh, let me see. Yeah, maybe.
Okay, let's discuss it more later.
Yeah, maybe. Yeah, some part of time to space can be discarded by this argument, or even can have some signal.
Yep. Thanks.
Okay, very good. Thank you.
Oh, yeah, one more question from Professor Kwanga.
Thanks for your nice talk. You may heard of the possibility of subsolar mass binary black hole made from dark matter particle. This idea requires very heavy mass for dark matter particles. Your conclusion is the mass, or the upper bound of the mass is 10 to the 6 electron volt, which is much smaller than the heavy mass in dark matter black hole idea. So I wonder whether this upper limit could be increased, or is there any way to increase this?
Let's see. Yeah, that's sounds interesting. I didn't think of this possibility from the beginning. So the question is how large M5 we can allow.
Right.
So if it's heavier than MEB, then we don't have to worry about BBN constraint and so on and so forth. Wow. Okay. I will try to figure it out later. So at the moment, I don't have any definite answer to you.
Okay.
Thank you. So what kind of mass range do you need?
Well, if I remember correctly, it was order of the GB, heavier than
so not that far from you.
Proton mass.
Okay, good. Okay, thank you.
Yeah, okay, it's time to move on to the next talk. Yeah, thanks again, Professor.
Thank you.
For a nice talk. And then, next speaker is Professor Kyu Jung Bae. Are you there?
Can you hear me?
Oh, yeah. Please share your screen.
Okay, so let me share my screen. Okay, so, sorry, I will reopen the Zoom again. Sorry.
Okay. The final speaker of this session is Professor Kyu Jung Bae from Kyungpook National University. He'll discuss about external dark matter. Please start.
Okay, thank you for thank Hyunmin and all other organizers for inviting me to this nice workshop. In my talk, I'd like to talk about a simple model to realize some feebly interacting dark matter in light of clockwork mechanism. So especially I try to think about some supersymmetric version of clockwork axion model. So As Koichi explained in the previous talk, the axion is a well-motivated theory to solve the strong CP problem. So from various stellar constraints and astrophysical constraints, we know that axion coupling is constrained by some intermediate scale f, the decay constant. It must be larger than around 10 to 8 or 10 to 9 GeV. So due to this small coupling, so axion is somewhat invisible. So, and then due to this small coupling and long lifetime, the axion can be a good dark matter candidate. So the SUSY is also a good solution to another fine-tuning problem in the standard model. It is called gauge hierarchy problem. So in the supersymmetric theory, we introduce SUSY partners of standard model particles, especially the partners of the neutral gauge bosons, the partner of photons and partner of weak bosons, and also partners of Higgs bosons. We can make some fermion partners. Then the lightest fermion partner, which is called neutralinos, can be a good weakly interacting dark matter candidate. So in axions and axion theory and SUSY supersymmetric theory, we have good dark matter candidates. If we consider the combination of supersymmetry and axion, we have another dark matter candidate. So in this model, we have to supersymmetrize the axion field to the chiral superfield, chiral axion superfield, consisting of the axion and its scalar partner and its fermion partner. Here, this fermion partner is called axino. It is another dark matter candidate in supersymmetric axion model. The axion itself is massless up to the chiral symmetry breaking because it preserves the shift symmetry. But its fermion partner and scalar partner become massive due to the supersymmetry breaking. But the size of contribution to the mass of axino is highly model dependent. I will not discuss about the size of the axino mass here. And this axino also inherits the feeble couplings from the axion coupling, the same as the axion coupling, axion-gluon coupling must be supersymmetrized, and this axion superfield and gluon superfield make the axino gluino-gluon coupling with the same strengths. It is suppressed by the 10 to 9 some scale f, which is larger than 10 to 9 GeV. So the axino is a good candidate of feebly interacting dark matter. So people might think about the origin of the such large scale, some intermediate scale, 10 to 9th or 10 to 10th GeV, to make the dark matter coupling is much smaller than the weak coupling. So the one good mechanism to realize such feeble interaction suppressed by the intermediate scale is a clockwork mechanism. So it is well-known clockwork axion model. People introduced a chain of n+1 pseudo-Nambu-Goldstone bosons, which I write here, phi 0, phi 1, phi 2 to phi n. So each clockwork gears coupled to each other by some constant 1 over q. And then at one end of clockwork gear coupled to the standard model sector. Here, for example, the phi n can couple to glue GG dual in the standard model with the coupling suppressed by some scale v here. So after the diagonalizing this sector, this phi 0, phi 1 to phi n, the lightest state here is almost the same as phi 0. So due to this clockwork coupling, the coupling of the lightest state to the standard sector is much more suppressed by a factor of 1/q to the nth power. So the lightest state coupling to the standard sector is exponentially suppressed. So we can realize feeble coupling from not so small coupling. For example, if the suppression scale, the physical suppression scale V is around 1 TeV, the Q is about 2, Q is 2, and we introduce the 21 clockwork gear here, n equal to 20. So we can realize intermediate scale for the lightest pseudo number Woodson boson coupling. So this is well-known clockwork axion model. So if we consider some supersymmetric version of this supersymmetric axion model, we supersymmetrize each pseudo number Woodson bosons to the chiral superfield, which includes the pseudo number Woodson bosons and its scalar partners and fermion partners, and all gears become supersymmetric chiral superfield, and it also couples to the SUSY version of GG dual. So from this supersymmetrization, we can get the chiral superfield with the clockwork structure. So if we consider the cosmology of this supersymmetric axion model, the axions in the axion sector, the lightest axion still massless because it preserves the remaining U1. So it is massless. It becomes massive after chiral symmetric breaking. So it can be a possible dark matter candidate if we consider the large misalignment angle. The heavy states, heavy axions, become massive. Its mass is generated by the clockwork gear, clockwork mechanism. So its mass is much larger than the QCD axion mass. So it is usually decayed before the BBN if the mass is around GeV or so. Those axions are also all heavy due to clockworking and also SUSY breaking. So it is usually heavier than the heavy axions. So it decays also before BBN. In both heavy axions and sexions decay to the standard model pair, for example, the gluon pair or photon pair. But in the case of axinos, heavy axinos are also abundantly produced due to this weak coupling suppressed by the TeV scale. But in the case of R-parity conserving model, subsequent decay of axinos into eventually the lightest axinos. So we can preserve the total number of axinos, then these heavy axinos are produced with a much larger coupling. So it enhances the lightest axino density. So let's see the detail of the model construction. So first, let me briefly review the axino production in the ordinary supersymmetric axion model. The supersymmetric axion model, the axion superfield interact with the gauge superfield like this way. For example, the axion superfield coupled to the gluon superfield here. So it makes the axino-gluino-gluon coupling. So in the thermal bath, for example, gluon-gluon scattering to the axino and gluino production is possible. So it produced the axino and also gluino, but gluino is in the thermal equilibrium. So the axinos are produced from this summer bath, and its final density is given by this formula. It is proportional to the re-temperature and inversely proportional to the decay constant F. So for the re-temperature is larger than the SUJI scale, especially the collisional mass, we can get this process, the dominant one. But in the case of the high scale SUJI, if the collisional mass or other superfield mass, superparticle mass is much larger than the re-temperature, or re-temperature is much smaller than the SUJI scale, then we cannot make this process because this is Boltzmann suppressed. Instead, we can consider the pair production of the exynos if the exyno mass is much smaller than the other superparticle masses. So we can get the effective Lagrangian like this way. We can just contract this mediating gluino, and then with this interaction, we can get the exyno density, which is this formula was derived by the Hyun-min and Ki-young about 4 years ago. So you can see here, it is very highly suppressed. It's very, very tiny number compared to the single production case. This is due to the double power of F here, and 1 over F here, and also suppressed by the gluino mass in the effective Lagrangian. So let me consider the Clark axiom model. So it is just a simple construction, just supersymmetrizing the well-known Clark axiom model. So we can consider the Kähler potential and superpotential here. So Kähler potential is just an ordinary canonical form of U1 charged field. And the Kähler potential, the superpotential, consists of this the interaction term, which describe the spontaneous U1 symmetry breaking and small explicit U1 breaking terms. If the small explicit symmetry breaking terms are 0, for example, this M prime is 0, so we have only this term, you can easily see that the n+1 number of U1 symmetries are preserved for the charge assignment shown in this table. So Z is charge 0, X is charge +1, Y is -1. So after spontaneous symmetry breaking, we still have a flat direction, X times Y equal to V square. So we can write this, we can describe this flat direction like this way. X times the capital X is some constant times exponential phi. Y is some constant times exponential minus phi. This phi describes the flat direction containing the Nambu-Goldstone boson phi here, and its scalar partner and fermion partners. Once the explicit breaking term M prime are turned on, the flat direction also develops potential. So it slightly changes the vacuum expectation value of Z and XY here. So the XY still satisfy this relation, but this small explicit breaking term fixes the value of X and Y here due to the potential. So we can write effective Kähler potential this way. So it develops a cosine hyperbolic potential of phi plus phi dagger and plus some small number times sine hyperbolic potential of phi plus phi dagger. And the effective superpotential becomes the cosine hyperbolic function of phi minus q, phi j minus q, phi j plus 1. So you can see here, n number of U1 symmetries are broken by positive non-zero m and m prime, but still one U1 symmetry remains unbroken. You can easily see that the shift symmetry phi j goes to phi j plus q minus j power times alpha, still respected by this superpotential. So this gives us a clockwork structure in the whole supersymmetric theory. So we can explicitly see the structure by seeing the effective potential in the quadratic order. So we can expand the cosine hyperbolic potential up to the quadratic order. So we can get this mass term of the chiral superfields. So there's some mass parameter times some dimensionless matrix shown here. So it is exactly the same mass matrix what we have known as the clockwork mass matrix. So it gives us the supersymmetric mass with the clockwork structure for all the chiral superfields. But we can also introduce the SUSY breaking, because in the phenomenological theory, in the standard model at least, there must be SUSY breaking. So we can also consider SUSY breaking effect in the axion sector. So it can arise in the superpotential like this way. It gives us the cosine potential for the pseudo Navier-Goldstone boson part, and cosine potential for pseudo Navier-Goldstone boson part, and this exponential potential finally becomes the cosine hyperbolic potential for the scalar part. So we can get the effective potential up to the quadratic order. So cosine hyperbolic for the scalars and cosine for pseudo Navier-Goldstone bosons. So this gives us the minus some mass scale times clockwork matrix for the scalars, and plus some mass scales times clockwork matrix for the pseudo scalar. So another SUSY breaking effect can appear in the Kähler potential. So it usually gives us universal masses for scalars. So we can just write the m sigma k square times identity matrix, and also fermions. So m psi k times identity matrix here. So overall, the matrices for the pseudo Goldstone boson and scalars and fermions are given by here. So for example, so first of all, so all those matrices are simultaneously diagonalized by the same orthogonal matrix O here. And then the matrix components are given in this formula. So this is well known, the clockwork matrix and the mixing orthogonal matrix. So here, so due to the clockwork structure, the zero mode, the lightest mode for the pseudo Navier-Goldstone boson is still massless because this lambda 0 is 0. But the scalars and fermions acquire the masses from the identity, the masses which is proportional to the identity matrix. So even for the zero mode, the lightest mode become massive due to the SUSY breaking effect. And also, I'd like to emphasize the sign here, the relative sign of the SUSY breaking effect in the pseudo-number Houston boson mass and also scalar mass is different. And also this fermion mass can be also negative. This m psi k can be either positive and negative. It can make some different mass hierarchy. I will discuss it later anyway. So the interaction terms of Xino can be described by the this coupling, the nth gear of the clockwork sector coupled to the gauge superfield. And then after clockworking, after diagonalizing all the chiral superfield, we can get the very suppressed, the exponentially suppressed coupling for the zero mode and the just order one coupling for the heavy mode here as the usual clockwork axion models. In the supersymmetric model, in addition to this coupling, we have the Xino coupling from generated from the Kähler potential. We got the cosine sine hyperbolic potential in the Kähler potential. It gives us a cubic power of 5 plus 5 dega. It gives us the Xino coupling and also Xino coupling. So the first one is usually responsible for the Xino production from some thermal bath, gluon scattering to the Xino pair production. And the second one is usually responsible for the Xino decay. The heavy Xino decay to light Xinos plus and axions. So let me consider the Xino dark matter. So our assumption here, to simplify the problem, the SUSY scale is much larger than the Witting temperature. For example, the gluino mass is much larger. And the sexion and Xino, the heavy sexion and heavy axion mass is smaller than Witting temperature, but still is much larger than the Xino masses. And also the hierarchy of the Xino masses the same as the hierarchy of the axion masses. It is possible when the m psi is positive. Let me remind you. So if this is positive, and after diagonalizing this the pseudo-Wollaston boson part and fermion part, we have the same hierarchy. The lightest Xino corresponds to the fibril coupling as the lightest axion. So the lightest mode is fibril interacting particle. Its coupling is suppressed by the exponential factor, and the heavy modes are weakly interacting. So in the thermal bath, these heavy modes are abundantly produced and subsequently decays to the lightest Xinos. So it's thermal production in our setup. The heavy Xinos are produced in pairs from the thermal bath. For example, gluon scattering to the Xino pair production. It is dominant process for the Xino production. There is also the Xino pair production through these sexion and axion mediated processes, and also sexion-axion decays through this coupling. But both the sexion-axion mediated processes are subdominant to the gluino-mediated processes. So the overall, the time average cross-section is given by this. It depends on the mixing matrices. And all produced heavy Xinos subsequently decays to the lightest Xino, whatever the decay path is. So it emits also lightest the zero mode axions. So total yield is proportional to the sum of this mixing matrix factor, but due to the clockwork structure, this O matrix is orthogonal, then this summation is exactly equal to 1. So you can easily see that the total yield of exynos are independent of clockwork gears and or the decay paths of heavy exynos. So the final exyno, the lightest exyno density, is given by this formula. So you can easily see it here. It is much larger than the usual single exyno, the non-clockwork model case. So in this same parameter space, in the single exyno case, for the decay constant 10 to 10 GeV, is the omega h square is 10 to minus 25. So we can have just 0.1 exyno coupling for the small read temperature around 40 GeV. So it tells us that regardless of the dark matter coupling, the abundance is enhanced due to the heavy mode decay. The heavy modes are abundantly produced because they are weakly interacting. So in the future, we can also consider the more detailed study of this model. The heavy modes are abundantly produced and it decays later to the lightest mode when emitting the zero mode axions. So due to this process, the lightest exyno can have some non-thermal distribution. It depends on the decay path of these heavy exynos, and it may affect the matter power spectrum of lightest dark matter component. And it can be observed by some observables. And we can also see some signals from emitted axions. And so we can consider some opposite case. If the mass matrix of exynos, if M psi is negative, then the hierarchy, the ordering of the exyno mass is inverted. So the feebly interacting component becomes the heaviest one. The all other weakly interacting components become the lighter mode. So in this case, the thermal production is not so much interesting, but we can consider some inelastic scattering between the light modes with a small mass gap. Okay, so let me summarize my talk. So exyno is a good feebly interacting dark matter candidate in the supersymmetric axion model. So feeble interaction may originate from the clockwork mechanism. So we can consider a tower of exyno states with this clockwork structure. So the lightest one is a feebly interacting and heavy modes are weakly interacting. So heavy exynos are abundantly produced and then decay to the lightest one. Due to this fact, the lightest exyno dark matter is its abundance is much more enhanced, and it is independent of details of the clockwork gears and decay paths. Okay, that's it. Thank you for listening.
Okay, yeah, thank you for the nice talk. Actually, time is up, but at the expense of break time, yeah, we can have a couple of questions. Yeah,
a question. I have a first question, two questions. One question is about exyno coupling. It is from the scalar potential that you said. So is the scalar part, I mean, if you imposed the shift symmetry only in the EFT, this scalar term is UV sensitive. So do you, I mean, in this scalar potential, what is the origin of this cubic interaction?
Okay, let me
maybe
quickly answer the question.
Yeah, you make some assumption on the in the renormalizable supersymmetric models.
Yes, yes.
And the second question is about the hierarchy between section mass and exyno mass, because those are from the Suji breaking.
Okay, so in the supersymmetric in the Yuan symmetry preserving limit, let's say m prime is 0, then this direction is flat. So there is no preferred value for a specific value for x and y, or any value is possible while keeping this relation. But when we turn on the m and m prime non-zero value, then it determines the ratio between this the vacuum expectancy value of x and y. Then if this x and y are different, so here you can see Xi, definition of Xi here, then we can get these cubic terms in the Kähler potential. Actually, this Xi value can be also changed when we introduce the SUSY breaking. You can imagine for example, the mass scalar term for these chiral fields, and it determines the potential along the flat direction as this m prime term. Then, after introducing the SUSY breaking, this Xi value can be different. Up to this point, this Xi is determined supersymmetrically, but after introducing the SUSY breaking, it can change, but still we can keep this shape of the potential. So in this analysis, I just put this Xi as a free parameter, but it's I think usually pretty small, but not exactly 0.
Mm-hmm. Yes. And also about because you need, I thank you very much for your answer. Another question is on the small axial mass, because I think you have spoiling the clockwork spectrum for sections and axino due to SUSY breaking, right? So
yes.
So those you are parameterizing them in your spectrum, right?
Yes.
So do you just do your assumption, or just say you have some justification?
As you know, it is highly model dependent for the axial mass and axonal mass. So my assumption is that after introducing the SUSY breaking effect, I don't want to spoil this clockwork structure. So this m prime parameter is small enough compared to the V, the Yuan symmetry breaking scale, and also the SUSY breaking effect in this sector is also very much smaller than V. And so my assumption is that these two factors are typically larger than this m prime contribution here, but still smaller than the weak scale, and much smaller than the Yuan symmetry breaking scale V. So it is my assumption to simplify the problem, but it can be larger than the weak scale, but at least to keep this clockwork structure, we have to keep in mind this SUSY breaking scale is smaller than the symmetry breaking scale V.
Okay.
So,
Okay. Yeah, it's time to wrap up. Yeah, this session. So, yeah, let's thanks to all the speakers of this session, and then having 2 minutes break, and let's resume the next session at 4 o'clock.
Okay.
Is there any announcement from organizers?
Yeah. As you said, let's resume at 4 p.m.
Okay.
Okay. Thank you very much. Thank you, everyone. See you. I will leave this Zoom